All right, recording is rolling. Welcome to Monday, October 18th. We're starting a new topic today, which is going to be energy and energy conservation. And so, you guys just turned in your centripetal force and gravity quiz, so thank you for doing that. Oh, I've got a cool animation to show you guys before I get rolling too far. So, let me switch my screen over. The present screen two. Thank you for that. And you guys are looking at, well, that is the Martian sky right there. That's what it looks like at nighttime on Mars. Wow, look at all the stars you guys can see. Now, why can't you see stars like that on Earth? Mostly because of what? Yeah. Okay, yeah, if you're thinking light pollution, that is actually a partial reason. There's a bigger reason, though, which is, yeah, exactly. Our atmosphere is way thicker, right? So mostly because we have a much bigger atmosphere. Like Mars has an atmosphere, but it's very, very thin. I forget exactly how it compares to Earth. I want to say it's like 1% of what we have on Earth, something like that. Yeah, and then light pollution is also an additional factor on top of that. Have you guys have ever been out in deep country, out in the middle of nowhere, and seen the night sky there? Yeah, you can really see a lot of stars, right? Now it doesn't look exactly like that, of course, but it's a little bit closer to that, right? Yeah, we've only had electric lighting for a little bit over 100 years, like as a civilization. So before that, people were seeing a much clearer night sky than we can see now. Okay. All right, so that was fun. Let me skip back over to projection. All right, so today and tomorrow, I'm going to give you guys a bunch of notes on energy. Power we won't get to today, but tomorrow. Right? But by the end of the day, I'll set you guys up with some conservation of energy. Okay? And you guys have a new homework page. Okay? It's clipped to the right side of your desk. Looks like this. Some of you guys found this already. So on one side it says Chapter 10, Energy Work and Simple Machines. And on the other side it says Chapter 11, Conservation of Energy. A lot of textbooks just push this all in one chapter, and I'm going to basically treat it that way. Right, we just it's all in one go, all in one section. So, yeah.
What is this new chapter called that we're on?
Energy. So chapter 10 is called Energy Work and Simple Machines, and chapter 11 is Conservation of Energy. But if you just say energy, then that's pretty encapsulating. Right, so the homework I'm going to pick up from you guys a couple of weeks from now, so not this coming Friday, but the following Friday, is well these problems from chapter 10 and these from chapter 11, and just like usual. I should have gone over these in class by that point. Okay. And then here's some bonus problems. So if you wanted to take advantage of the bonus, just like we've been doing all along, I think this has been a pretty good system working out. Then we'll just keep doing that. All right. Questions so far? All right. Now I did throw a question over here that you guys do see this leaning tower, right? You're dropping something off leaning tower. So what's the speed as it's hitting the bottom? And the reason I'm throwing this question here is because this is something that you guys are already like very familiar with. This is a story that keeps recurring in this class, isn't it? Like Galileo drops stuff off the tower. Right? We analyze this like a million different ways. This is actually a pretty good classic fundamental example of what we're about to get into, which is energy and energy conservation. Because the speed at the bottom, you guys already have a way to solve using kinematic formulas. You guys remember these three amigos right here? Maybe this bottom one. Maybe by the end of class today, this is going to come back and I'll show you guys that with a new method, conservation of energy, it's a different approach, different thought process. You can also get this answer just from a different point of view. Now, conservation of energy, you can use to set up all kinds of equations and solve all kinds of problems. Some that you already have ways for, but sometimes faster. There's some kinematic. There's some problems you can solve using those kinematic equations. It just takes a long time, a lot of paper. And then with conservation of energy, you can solve them really fast. And then there's some problems that are going to be like novel to conservation of energy processes. Right? So let's get into it. We have a new variable and a new unit. Right, so energy is measured in joules, which is capital J. Okay. So energy is your new variable. And joules, well, that's a unit, right? That's an SI unit, like a metric unit. Okay? Now, some things I want you guys to know about energy. This is a scalar quantity. You guys know some scalar quantities, like mass or time, even we consider to be a scalar. Okay, so it has a magnitude, like some number you can associate with it, but direction is not really important. Okay? So yeah, this is in contrast to a vector, where direction would be important, but for energy, it's not. Okay? And then, well, I'm going to list a really important point here that's going to come back in the notes by the end of today, which is that energy is conserved within the universe, which means that you can't create or destroy it. You can transfer it from one form of energy to another form of energy. And I'm going to give you guys a bunch of forms today. Okay. So later on today, you guys are going to see this. The sum of energy in some initial state is equal to the sum of energy in some final state. Okay. Let's say that all the amount of energy in the universe, say all the number of joules, if you were to quantify it, that have ever been, is all that there have ever been, and there will never be any more or any fewer. So what is one joule? This quantity that's somehow not created or destroyed in the universe. It's just conserved. Okay. Well, 1 joule breaks down into 1 Newton meter. Okay, so it's a composite unit. You guys might remember our first couple weeks of class, I told you that there are 7 fundamental units, 7 fundamental ways to measure things like mass in kilograms, or displacement in meters, or time in seconds. Right, those are 3 of them. Okay. And then we have these composite units, right? We start to build up units like building blocks. Like, you guys know that 1 Newton is 1 kilogram meter per second squared. Right? Isn't that consistent with F equals ma, like Newton's second law of motion? Okay. So if you put this all together, then 1 joule, if you break it down to its very fundamental components, it's this. It's 1 kilogram meter squared per second squared, because the meters combine. Ooh, okay. So units of energy, right? So if you pump a gallon of gasoline into your tank, that gallon of gasoline has some amount of energy that's going to carry the car so far. Okay. You could quantify it into some number of kilogram meters squared per second squared. How about you flip on a light, right? And say a light bulb's been burning for an hour, right? There's some energy associated with that you can quantify in kilogram meters squared per second squared. There's some power plant on the other end that had to supply that, right, through the electric grid. Suppose you eat breakfast. There's some number of calories that you get out of your food. Calories is an alternate way to measure energy. So 1 calorie, I want to say it's the amount of energy required to raise 1 gram of water by 1 degree Celsius. And you can convert back and forth between joules and calories, but we're not going to worry with calories so much. You just got joules. Okay? Most of the rest of class today, I'm going to give you guys some, what I'll refer to as building blocks of energy. Kind of my own Griffin colloquialism to talk about energy. Okay? But there are certain forms that energy takes, and then by the end of class today, we'll start setting up energy conservation, or at least one. Okay? Actually, the very first one I'm going to give you guys is, maybe doesn't fit in this list super nice, but you guys see. I'm going to call it work. Now, work is not really a form of energy so much as it's a transfer of energy. Maybe from one object to another object, maybe from one system to another system. Okay. It's going to have a formula associated with it, but we'll hit that in the notes pretty soon. Okay. After I talk about work, I can tell you guys about gravitational potential energy. I'll tell you guys about spring potential energy. Energy stored in a spring, like maybe a spring's compressed, it's got some energy, like spring loaded, ready to go. And then finally, kinetic energy, which is like energy of motion. So if something's in motion, there's a certain energy that's associated with that. Again, this is a formula attached to it. Okay. Now, these basic building blocks, does this represent all the kinds of energy that could ever be in the universe? No. not at all. So I'm totally missing like chemical energy, like energy stored in a AA battery, or like food for that matter. Right? There's no nuclear energy here. There's no thermal energy. Okay, so energy could definitely take other forms. Usually these are called mechanical energy. Right? So mechanical energy. And these are the types that we're going to care about for this class, so we can set up some basic conservation of energy equations when we eventually get there. Okay. All right. So let's start with that first one, work, right, which I just told you guys was a transfer of energy. If you do work on something, it's like you're putting energy into that thing. Okay? And there's a formula for it. It goes like this: work is equal to, you know what? Right before I show you guys the formula, I bet you guys can figure it out based on something that I already wrote. Remember I told you guys that 1 joule is 1 Newton meter, right? If you know this, then work is really just this turned into variables, because 1 joule could be like energy, like an energy transfer work. Newtons and meters, hey, isn't that force and distance? And that's exactly what this formula is. It's just force times distance. Okay. Now notice I put a big old dot between the F and the D, and there's a specific reason that I did that, and I'm about to tell you guys why. I just label these parts. If you push or pull on something for some displacement, I might say distance, but you guys know, something like that, right? Now, force and displacement, those could both be vector values, right? But I told you that energy, or work for that matter, is a scalar, right? It doesn't really have a direction associated with it. Okay, so when you multiply vectors together, there's actually different ways to multiply vectors together and different interpretations of that. And one process is, well, involves this dot. This is called a dot product. So dot product. And it's a form of multiplication. And what it means is that, you have to write this over here, okay? You only multiply parallel components. Okay? Only of the 2 vectors that are being multiplied together. Okay? So sometimes it's written like this: work equals, this would be true of any dot product multiplication, but this would be a specific example. The magnitude of the force times the magnitude of the displacement times the cosine of the angle between those 2 vectors. Okay? That's the exact same thing. Okay? Like this box and this box say the same thing, just the bottom one's spelled out a little bit more explicitly. Okay? So I'm going to give you guys an example that's going to make this make sense, because some of you guys might see that and say, okay, I can kind of get what that means. And some of you guys say, I probably need to see a picture, see an example. Okay. So let's look at a shopping cart being pushed across the floor. Okay. So got the shopping cart, got its wheels. Okay. I'm going to make a partial free body diagram. Okay, so let's say that we're pushing this cart. Well, if you're pushing straight horizontal in the direction of motion, then the amount of energy you transfer into the cart, like the work you do on it, is just very simply the pushing force times however far it rolls. Okay. But what if you aren't doing that? What if you're pushing it kind of down at the same time, which is maybe a little bit more realistic, right? So you're pushing down with some force, right? And as a result, you move the cart like this distance, d, something like that. Okay, how much energy did you transfer into that shopping cart to move it that distance across the floor? So the floor keeps going. Draw that in. Okay. How much energy did you transfer into the cart? Say, how much work did you do on the cart? Okay. Well, do you guys see that the only component of the pushing force is just the parallel component, like the component that's parallel to the floor? Okay. So maybe I need a reference line, and I need to break this force vector into components, right? And this is something you guys have been doing for a long time in here. Oh, here's theta. I think, oh yeah, you guys' very first quiz, I said, hey, break triangles into components and make sure you can do that, because this keeps coming back over and over again throughout the, yep, here it is again. Breaking a vector into components. Keeps coming back. But you guys have done a bunch of these in this class, so you guys know that this parallel component is equal to what times what? Force times sine or cosine of that angle. Cosine, yeah. Okay. And the downward part, the part you're pushing down, well, that must be F times sine of that angle because it's opposite of the angle. Right? Guess that? Right? Now, that amount that you're pushing the cart down, that's not actually moving the cart forward, is it? Right? If anything, it's actually impeding the motion of the cart because that would cause the normal force to increase, which if there's friction, that would also cause friction to increase. But either way, it's definitely not helping the cart move forward. Right? Now, remember, I said this is a partial free body diagram. I left off with those other forces. I didn't draw the normal force. I didn't draw the friction force, but I'm just focusing on the part that matters for this. Right? Right. So I think that the say if you had a question like how much energy did or was transferred into the cart, how much work was done on the cart. I'd say, well, work is equal to just the cosine component of the force, so cosine theta, multiplied by the distance it was moved, which is d, and oh, hey, look at that. That's the same thing as F times d times cosine theta. Just shuffle things around a little bit, which is the same thing as the definition of work I gave you up here, which is this dot product. Right? You guys see that? Do you guys see how dot product works now? Right? Just the parallel components that matter. Now, dot product would be in contrast to something called a cross product, which is a different way to multiply vectors together. So when we get into rotation, well, we'll go back and talk about rotational dynamics, and then I'll come back in a different context. Okay. Right, you guys good so far? Okay. Let me give you guys a counterexample to, well, maybe an extended example, but just sort of like the opposite extreme. What if you had a book, like a textbook? And let's draw a free body diagram of this textbook. So it's got a center mouse right there, and you're just holding it at rest, holding this textbook at rest. So this thing has a weight acting straight down. This thing has maybe a force from your hands holding it up. And if you're holding it at rest, that would be the entire story, wouldn't it? I'm going to throw in some numbers, just to, you need some numbers, this might help. What if the book weighs 20 newtons? Okay, well, you must be applying a 20 Newton force just to hold it up at rest, right? Okay, now what if you take this book and you carry it horizontally across the room, some distance, 5 meters? The question would be, how much work was done on the book to move it, so moving it 5 meters horizontally. Okay, so horizontally, let's say constant velocity, right? So you're just moving across the room. Hey, guys, if you're moving something horizontally at constant velocity, does it need any horizontal forces? No, I mean, maybe an initial force to get it going, but once it's in motion, it's kind of like Voyager spacecraft, right? It could be this exact free body diagram right here, this free body diagram. This free body diagram might refer to a book that's moving at constant velocity in some direction. That's okay. But see your applied force, which is the 20 Newton upward force, in that distance it moves horizontally, 5 meters. Do those have any component that's parallel to each other at all? No, they're perpendicular to each other. So the applied force upwards and the distance moved horizontal, right? Those have no components that are in common. Therefore, how many joules of work were done on that book? 0. 0 joules. No work. Okay. There's no work to move it horizontally. Now moving it vertically is a different story, and that's where I'm taking these notes next. right? So maybe see if I can prop this side by side, maybe we can fit this on screen. Right? So the next set of notes, just gonna redraw the book. Same free body diagram. And so it's got a weight down. Let me give you guys a number, 20 newtons, just like before. And your applied force from your hands, would be 20 newtons to hold it up. But this time, let's say you're moving this book upward a distance of 5 meters. So So say distance that goes 5 meters vertically. Okay? So how much work to lift the book vertically? 5 meters. Let's say you're just lifting at a constant velocity, which would be exactly consistent with that free body diagram. FBD, free body diagram. How much work? Okay. Well, this time, force and displacement are exactly parallel to each other, aren't they? They're in the same direction. Like they're both up. They're pushing up, and the book is moving up as a result. Okay. So the answer is work equals force dot distance, which is a 20 Newton force for 5 meters vertically. That is 100 joules of work. It takes 100 joules to lift it. Okay? So there's no energy input required to move it horizontally as long as there's no horizontal force. Okay? If the force is vertical and the motion is horizontal, there's no energy transfer associated with that. Okay? But if you're pushing up and the book is moving up, then you're transferring some number of joules into it to lift it. Okay? Now, take a look at this expression here. Work is force times distance for moving upward. Right? For this exact example, isn't the force also equivalent to the weight of the book as long as it's just in equilibrium like this? Okay. So, I wonder if you could do this. Instead of force, what if you replace that with mg? Because, I mean, that is equivalent. Okay. And then instead of distance, well, I mean, it is a vertical distance, so that could be called height, couldn't it? Right. And look at this expression, mgh. So the amount of work that you did on the book is also equal to mg times h. Okay. That is about to be the next page of notes, the next building block that I've been calling it. Okay, you guys ready for the next building block? Oh yeah.
Can you explain again why it's 0 joules when you move it horizontally?
Okay. Yeah, when you move it horizontally, why is it 0 joules? Because the application of the force and the displacement that it moves have nothing to do with each other. Okay, so once it's the motion, you might think of Voyager spacecraft or maybe an air hockey puck. Suppose it's already in motion. So now to get it in motion in the first place, yeah, you do have to do a little bit of work to do that. But that aside, once it's already in motion, moving horizontally, you guys know that an air hockey puck will just keep on going horizontally forever as long as there's no friction, right? Voyager spacecraft is just going, right? It's just going. Right? There's no energy to keep it that's necessary to keep it going. So same story there. Right? The application of the force, vertical, and the motion, horizontal, just have nothing to do with each other. Right? Kind of like, back to last page, when you're pushing a shopping cart, the amount that you push the cart down has nothing to do with propelling it forward. Right? So that part doesn't count, right? The only components that matter for force and distance for work are the force and distance that are parallel to each other, just the parallel components. Okay? Okay. Like that. Okay, which means that, yeah, if you're lifting it, then you are transferring energy into lifting it. Okay? So suppose you've transferred this much energy into lifting it. Well, that means that that book would have, say, 100 joules of energy after it's been moved up 5 meters. That energy has a name, and that's the next building block here. It's called potential energy, or, well, more properly, I guess, gravitational potential energy. Now, usually I drop the word gravitational and just call it potential energy, although there is another kind of potential energy, but we're getting it. Now, the unit for the variable, I should say, well, there's two that I'm going to give you guys, well, sort of. So you might see PE to refer to potential energy. Some textbooks say this, some pages that they give you guys, some old handouts might say PE for potential energy, which is maybe kind of intuitive, but the problem with that is that it'd be really easy to mistake that as two variables multiplied together, which it is not. So let me say, or what I've been trying to transition over to, and AP has also done this, is just use capital U. So whenever you see capital U, that represents potential energy. Right? Sometimes you see U with a little subscript G to specify, well, specifically potential energy against gravity. I mean, like if you're lifting this book against gravity, right, then that's the type of energy that would be associated with that. Right? And the formula is exactly the end result from the last page of notes, the amount of work done on the book to lift it to some height. It's just MGH. That's it. MGH. That is the next building block. MGH. Okay, okay, so you guys know U is potential energy. M is the mass of the object. G is the gravity field, like 9.8 meters per second squared. And H is the height above, well, I'll say ground level. Okay, like that. That's the energy associated with being lifted some height in some gravity field. Okay? Now, a couple of things with this. If something's just sitting at rest, like some height above some floor, okay, what this formula is saying is that it has some energy, some quantity of energy that's associated with that. So let's take that textbook, just pop it right on the edge of this lab table where it's just teetering right on the edge, right? Well, if this book has some mass, and it's above the floor, some height h, and it's in some gravity field g, supposedly there's energy associated with that? Well, what does that even mean? Okay. Well, what if you nudge this book a little bit, you know, tip, and what, shoom, crash into the ground? Okay. When it crashes into the ground, it's definitely got like motion, like some speed. It's going to hit the floor with a bang. In fact, the higher it is off the floor, the more the impact. But that energy had to come from somewhere, and I'm getting to the principle of conservation of energy. So where did that energy come from? Well, it had something to do with, well, the fact that it was a mass and some gravity field at some height above some point. You could quantify it that way. Right? That's the amount of work that it would take to lift it to that height in the first place. So that's the amount of energy associated with that. Right? Now, this gravity field, do you guys remember from the last couple of weeks that this 9.8 meters per second squared is really only true in the vicinity of the surface of the Earth? So if you tunnel way down deep into the Earth, or if you take off in a rocket and get further away from Earth, this number definitely changes. So this is actually a localized form, I'll say localized form of potential energy, localized to the surface of some planet. Okay. Probably tomorrow, I'll tell you guys the universal form, which this is actually a simplification of, as long as your height changes small relative to the size of the planet. Okay. And the last thing I want to say about this is that it has to do with this h, like this height above the floor. Okay. Now, when I was going through physics first time, I was always scrutinizing every formula that I was given and saying, is there any kind of internal inconsistency? Well, there never is, by the way. I mean, spoiler alert, but I was always looking for something. Really checking these equations and saying, does everything make sense? And this one I had trouble digesting because I was saying, well, okay, yeah, maybe this book could drop. Like, yeah, let's do a real life example. I got a textbook right here. I could set this, I could prop this at the edge of this table. You guys see it's probably pretty close to a meter off the floor. It's about a meter off the floor, right? So this would be height 0 at the floor. You could take mass of the book times gravity field times that 1 meter height. Okay, get some energy associated with that. But here's the problem. What if you dug a hole in the floor right here? Just dug a hole in the floor. And then we could see below us, the floor below us. Wouldn't that be several more meters it could drop? Then the height above that floor would be much bigger, maybe like 3 or 4 times as big. And you would be changing the potential energy of the book without ever touching the book, right? All you'd be doing is just, whether the book falls through the floor or not, or sorry, through the hole in the floor, kind of different definitions of potential energy. How's that add up? It turns out it's all okay because of this. You're actually allowed to define height 0 wherever you want, and as long as you're consistent within some problem, so, like some equation that you're setting up, then everything will check out. So you could define the height of the floor, height 0 right here, and if the book falls to the floor, then the mathematical interpretation is that it just moves into negative territory. And you could actually treat it as having negative energy, which is kind of a weird concept, but mathematically it all works out all straight. Okay. Alternatively, you could actually change the definition of height 0 to several meters below, like wherever the ground floor is beneath us. And then this would no longer be height 0, it would be height so many meters. But the potential energy of the book, say if it went from here, like crash land on this actual floor, what's important is that height change is what matters in the equation, which ends up just being the same. So yeah, this checks out. And just in case you had like the same scrutiny as I did back when I was sitting in your position, is when we get to the equations and set it up, then everything's gonna work out fine. Okay. All right, let's look at a graph of either work done on something or say potential energy something could have. So here, show you guys a couple stories and we'll make a graph for those stories. So either you push a cart with a constant force for some distance, or lift a textbook of some weight, some height. Okay. So we're going to draw one graph that could actually apply to either of those stories. We're going to do a force versus distance graph. So force measured in newtons and distance measured in meters for the axes. Okay. Let's say that force is just very generically F for force. Okay, great. Okay. And the distance that either you push that shopping cart or that you lifted the book, we'll just call it some very generic value D. Okay, so push some constant force F for some distance D, great. Okay. We got a rectangle. Ooh, rectangle. You know what? I remember back from kinematics section that when we were doing graphs, remember graphs could tell multiple stories depending on what property of graph that you're looking at. Like in this case, you could know like different forces, but it's all the same force. Right? But I wonder if there's some other property of this graph that you can get. Like from a V versus T graph, you can get acceleration as the slope or displacement as the area. You guys remember that? Huh. Take a look at the area of this rectangle. I wonder if that area, this area, represents some physical quantity. Okay. Let's see. There's the height of this rectangle is in newtons, and the base is in meters. You guys see that? Some number of newtons times some number of meters. So if you do like base times height for the rectangle, that would be some number of joules, wouldn't it? Okay. Also, I gave you guys a formula said work is force times distance. We've got force, constant force for some distance, all in the same direction. That's what this area represents. It represents the work done on some object, like the energy transferred into it, moving it. Okay. Right, now, why am I bringing up this graph right now? Because there's a slightly different graph that's going to lead to the next building block, and it has to do with springs. So let's go back to Hooke's law. You guys remember those springs? Okay, I don't have a spring scale within reaching distance right now, but I actually got one of this little pen right here, so maybe I'll use that as an example. So you guys remember springs? It can have some spring constant that's associated with how stiff it is. I think one day I took those spring scales and we figured out what the stiffness was with each of those spring constant. Okay. Let's say you compress it some distance x. So the spring used to be this long, and now we're gonna like compress it some distance x. So spring constant is k, and the compression distance is x. You guys remember Hooke's law says F equals KX. You guys remember that? Okay. Now, I've been saying compression, but it could be stretching a spring. This would also work. Some textbooks throw a negative sign on there, but it's all a matter of perspective. Let's just do the positive value. Okay, so what does this graph look like? On maybe like the same sets of axes that we just did. Okay, so force versus distance. This could also be force in newtons versus compression distance. mean, I could call it X, but it's the same thing as D, right? Now, what does this graph look like? Can you guys draw this graph before I do? Because you've drawn it before. I mean, F equals KX. Isn't that like Y equals MX? Isn't that just that relationship? That's a direct relationship, isn't it? Slope K. So slope K, F equals KX. You guys good? All right. Now, if you compressed the spring up to some value X, then the force on it would be equal to Kx. That's what force would be, because F equals Kx. And that graph would look like a triangle. The area under the curve, I should say, would be a triangle. Isn't that true? Okay. So here's what I'm getting at. I'll show you guys with the spring, since this is one I got right here. Okay, so here's the spring and this pin. Okay. Right now it's completely unstretched. There's no force on that spring. There's no energy stored in the spring. But if I take this cartridge and I push that cartridge into that spring, it takes more and more and more force. The more force I push, the more it compresses. Do you think there's some energy stored in that spring right now? Ooh, I bet there's a term for that. I bet that's called spring potential energy. And I could get that all back out just by releasing this cartridge. It'd go, pew, it would fly off, wouldn't it? Right? So we're talking about spring potential energy. And you know what? That spring potential energy is exactly equal to the area of this triangle. So that area represents the energy stored in the spring. Tell you, or equivalently, it's the work done to compress it to that distance in the first place. Okay. Is that all right? Okay, so that's a graphical approach in comparing it next to just the traditional force times distance, right? Because this is a variable force now. Okay? Okay, so the base of this triangle is x. The height is kx. So how much energy is stored in the spring? So energy stored in the spring. That's called spring potential energy. Right? It's energy that could potentially be recovered. Okay? And that's U is potential energy. I told you that a few minutes ago, but I'm going to throw a little subscript S on that. Okay? And well, it's the area of that triangle. So 1/2 base height, right? 1/2 base height. The base was some value x. The height was some value kx. Here, bring it side by side so you can see that. Okay. So 1/2 base height for a triangle. Base is x. The height is kx because Hooke's law. Okay. Hey, and then can you just consolidate those x's and you get the energy stored in the spring is 1/2 kx squared. Ooh, so now we got another building block. Oh, great. So energy is taking all these different forms. We had work was a transfer of energy. There was gravitational potential energy, which was actually pretty close related to that. Now we got energy stored in a spring, which is following a similar thought process. You guys good? Okay. One more main building block. And this is kinetic energy. Kinetic energy. This is energy of motion. Energy associated with motion. If something has a velocity, like a speed, actually velocity is not even so important, just speed, right? Because remember these are scalar quantities. Okay? Then there's energy associated with that. Now, kinetic energy, if you guys get an old handout, it might say KE on it, but I've been trying to just use plain capital K. Okay? Now, be careful, because capital K could be kinetic energy, but lowercase k could be spring constant, so don't mix those up. It might be easy to do that. Okay? So what is this energy associated with motion? Okay, well, here's the formula for it. Kinetic energy equals 1/2 mv squared. And as you guys are writing that in your notes, make sure that you're using a capital K, nothing that you could confuse with a lowercase k, because we're talking about kinetic energy here. Okay. Now, what's the derivation for that? Like, where does that come from? So I'm saying 1/2 times the mass of some object times its speed squared. Okay? That's the kinetic energy. Where does that come from? Okay, now this one, I don't know if I have a great explanation for you guys, but maybe I've got two explanations. One is I'm about to draw you guys a graph that you could sort of argue leads to that. And the other explanation is that I'm going to go back and talk about that Galileo dropping stuff off Leaning Tower Pisa and show you guys that it comes out to the same answer using this equation for kinetic energy as you did using those kinematic equations from back in the day. So it's still consistent with everything we've done. Okay. The graph I'm going to have you guys do is momentum as a function of velocity, right? Which I know we haven't even talked about momentum yet, but momentum is just mass times velocity. And if that's true, so as you speed something up starting from rest, I mean, this graph will necessarily be a direct relationship. Right? It couldn't be anything else. It has a slope that's equal to the mass of the object, right? So mv is just m times v. Right? And what's interesting about this, though, is that, well, this vertical axis has units of kilogram meter per second, or if you like, Newton seconds, it's the same thing. Okay. But the horizontal axis has units of meters per second. Right? Anyway, the area of this triangle is some number of joules. Right? It takes some number of joules of work to speed up some object to some speed. Right? In that area of the triangle, if you work out math, it's up being exactly that expression. It's the same thing. Okay. Guys, all right? All right. Oh, now let's take those building blocks. Here, flash you the notes. We got kinetic energy, energy of motion, 1/2 mv squared. You got energy stored in a spring, 1/2 kx squared. There's potential energy, well, gravitational potential is mgh, and work is force times distance. Force times distance, which is a dot product, right? So just the parallel components of that. Okay. So what are we going to do with all these building blocks? All these building blocks of forms of mechanical energy. What we're going to do is use them to solve conservation of energy equations. So conservation of energy. Now, conservation of energy means you can't create or destroy energy, which is some number of joules. Right? So if there's like 100,000 joules in a system and say it's a closed system, then you can do any crazy process within that system, but it's going to be the same number of joules. You are allowed to transfer, so you can transfer from one type to another, from one form to another. Okay. So, for example, from potential energy to kinetic energy, and that's what we're about to look at. Okay. So, conservation of energy, I can write like this: the sum of energy in some initial state is equal to the sum of energy in some final state. There's your conservation of energy. So, sum of initial energy is equal to the sum of final energy. Which is actually a thought process that you're somewhat familiar with from kinematic motion stuff, because we were always going from some point A to some point B, some initial to final. Okay, so same story here. Let's tackle this Galileo problem, dropping stuff off Leaning Tower, from this using this new method. Right, so here's the first conservation of energy that I'll do with you guys. Galileo drops something, crash lands on the ground. What is the speed of that crash land? Well, we're going to go sum of energy at the top of the tower is this equal to the amount of energy at the bottom of the tower. Okay? Now, if Galileo drops this ball, then what type of energy was associated with the very top? Wouldn't it have to be potential? Something to do with its height? So that's just potential energy at the beginning, and nothing else, as long as you didn't throw it. Okay? And at the bottom, well, there's definitely kinetic energy because it's in motion, it's moving really fast. Okay? But there's nothing else. There's no potential energy anymore at the ground level because its height's gone, so it's just that. I can call this mgh. I can call this 1/2 mv squared. Right? Just pop in those building blocks. Right? Looks like the mass of the ball is going to cancel, which is consistent with what you know from kinematic motion. Can you solve for this v? Well, cross multiply up to 2. So b squared equals 2gh. And take the square root, root 2gh. Let's plug in some values. So, tell you what, I hate to do this, but we got 2 minutes till the bell, so here's what I do. I'm going to show you guys this, I'm just going to flash notes up here from last class. Right? So if you take this, v equals square root 2gh for the Galileo problem, and you plug in some numbers. Suppose the tower was 50 meters tall. Let's use 10 meters per second squared for the gravity. Then would the speed come out to be like this, right? 31.6 meters per second. This is the new method. What was the old method? The old method was to use these kinematic formulas. You guys remember these right here, right? And this third one's the most useful. You could show this as a solution to the first two system of equations to get this one. Talk about that. Okay. Then so look, bx squared equals b naught squared plus 2ax. You can plug in the same values. Acceleration is, well, there's Earth gravity. The height change, x, would be 50. Hey, it comes out to the exact same thing. Right? So 2 different methods now. Here's the old method, here's the new method. Yes, it comes out to the same thing? Is that? Now, for now, that's nice. Like, we've got an alternate method, but again, I'm telling you guys that sometimes this method is faster than the old way, and sometimes it allows you to solve for stuff that you couldn't before. And last thing I'll say before you guys take off today is, remember that whole potential energy equals mgh, right, which we were just looking at? Well, that g, remember I told you guys to localize. If you get too far away from Earth, then, well, that starts to change. So there is a more universal form of gravitational potential energy, which takes this form. And it turns out that mgh is a really good approximation as long as the r change is not very big. Right? So I'll talk about this more in the future, but I just want to leave you guys with that for food for thought for now. All right, any questions, anything from today? All right, you guys have a good Monday.